Okay, in this lecture, we're going to be going over measures of dispersion. We've got information here on three different measures of dispersion. The first measure of dispersion is the one that we use the most often, and that is going to be the range. This is definitely by far the simplest of all the measures of dispersion. Because it literally only considers two values. The range considers the maximum value and the minimum value. So, for instance, if you have, the a dispersion or a group of data that, for instance, I think we're going to be doing a lot with ice cream cones today. So, if you've got a group of data, and more specifically, a group of data focused on the weight of ice cream cones, and you've got the maximum weight of an ice cream scoop of 8 ounces and a minimum weight of an ice cream scoop of 2 ounces. Then you've got the range. The range is literally the max 8 minus 2, the min, and the range then equals 6. So it's only influenced by two values, and so there's definitely some issues with that, but it can also be really easy to calculate. So that's the range. And then we've got the standard deviation and variance. So we've got the standard deviation there, and we've got the variance here, and the standard deviation and the variance are very similar. So if you take a look at this, on the left-hand side, you're going to see the sample data. Then on the right-hand side, or sorry, the sample formula. On the right-hand side, you're going to see the population formula. And you'll notice it's not that different. It's pretty much all the same, except we are dealing with English letters here, and we're dealing with Greek symbols here. And then also on the bottom, there is n minus 1 as compared to n. Capital N is signifies, hey, we're dealing with the entire sample number, the entire sample, not just a population, where n minus 1 says, hey, let's take the number in the sample and let's subtract 1 from it. And there's a lot of really good information on Canvas about this. I might even put a link in below that talks about why we do n minus 1, but we're not going to get into that for right now. And so you'll see right up here it says, okay, S stands for sample standard deviation. Oh, but wait, we're not dealing with the standard deviation right now. We're dealing with the variance. But what's important is the variance is literally the standard deviation squared. And so when you see lowercase sigma squared or s squared, really what we're saying is we're saying this squared standard deviation, or we're dealing with the variance. Okay, and then we go through each one of these, and I've got a whole lecture just on calculating this by hand. But we're going to get a little bit more into the empirical rule and Chebyshev's theorem in this lecture. So if you want to go into watching this by hand, by all means watch that lecture. So variance is good, but at the same time, the reason why we don't use it is because it's not actually in real world metrics. It's in squared metrics. So you're taking the average distance from the mean and squaring it. It's like walking around and saying, hey, I'm, let's see here, 12 times 6 equals plus 2. So I'm 74 inches tall. And so stating the variance would be like the equivalence of saying, okay, I'm 74 inches tall squared, or 74 times 74 equals, I'm 5,476 inches, I'm the, squared, or this, I am the square root of 47,000, or 5,476 squared inches. So, like, if I were to walk around telling people that my height is the square root of that, it really wouldn't make too much sense. So that's like the same thing with variance. So, moving on, we've got the sample standard deviation and the population standard deviation. Let's get the sample is on the left side, population is on the right side. Same thing as the variance formula. The only difference is now you're taking the square root, and when you're taking the square root, it puts it into the real world score. The real world score, where it literally is the average difference or the average distance of each observation from the mean. Okay, so it's in the original, the real world metrics, and it can never be negative. That's important. And it is the most widely used spread of dispersion. So let's take a look at an application of this. Why do we care about the standard deviation? Why do we care about the average distance that each observation is from the mean? The reason why we care about that is, say for instance, you wanted to know, okay, I am going to look at this information and I want to know how many observations are within this range of values, or what percent or what proportion of observations are within this range of values. And so I've got a situation right here. I've got Chebyshev's theorem. Chebyshev's theorem basically says for any set of observations, sample or population, the proportion of the values lies within k standard deviations of the mean when of the mean is at least 1 minus 1 over k squared, where k is any value greater than 1. So what does that mean? Okay, what that means is the proportion of observations that lie within a certain number of standard deviations from the mean can be calculated with this formula. 1 minus 1 over k squared. 1 minus 1 over k squared. So if you take this and you do 1 minus 1 over 2 squared, notice it says here it's got to be, where does it say that? It's got to be, k has got to be greater than 1. So 2 is greater than 1, so 1 minus 1 over 2, or 2.5, will give us the proportion of values that will be within 2.5 standard deviations of the mean. So we do 1 minus 1 over k squared, which is 1 over, so 2.5 squared, which equals 1 minus 1 over 6.25. And if you calculate 1 over 6.25, let's do this. 1 divided by 6.25, that's going to be 0.16. So now we take 1 minus 0.16, and that is going to give us 84, or 84%, or 0.84. What this is saying is that we know that at least 84% of individuals, of lawyers' starting salary coming out of law school, will be within 2.5 standard deviations of the mean. Well, that's great, but who really cares? You know, am I going to go in and say, hey, this is the average starting salary of lawyers is going to be within, that 84% of lawyers' starting salary will be within 2.5 standard deviations of the mean? Nobody really cares about that. So what you're going to want to do, is, let's come down here and we're going to do, let's see here, 2.5 multiplied by the standard deviation, and then we're going to subtract, we're going to take the mean minus 2.5 standard deviations, and then we are going to do mean plus 2.5 standard deviations, 2.5 times standard deviation. The standard deviation is right here, which that's a very large standard deviation, and I'm about to show you in just a minute why that's so large. Control V, so it's going to be 33 and 33, which 2.5, let's do 2.5 multiplied by 33,043.43, 43. So it's going to be 82,608.58. Okay, so we are going to do the mean plus that and the mean minus that. So what's the mean? The mean is 71,299. So what I did is I did 71,299 minus that 82,000, which equals 0. And the reason why is because you can't have a negative. We can't have a salary that's a negative. And then the mean of 71,299 plus the 2.5 multiplied by this equals $153,907 0.61 cents. So what Chebyshev's theorem basically says is it does not matter what your distribution looks like, regardless of what your distribution looks like. It can be a crazy distribution, and even if it's a crazy distribution, Chebyshev's theorem should still hold true. There shouldn't be an issue as long as you calculate everything correctly. And so let me show you why I specifically chose lawyers. Okay, so I'm going to, let's see here, pull the data set up right here. Okay, so this is the data set. This right here is a spreadsheet of the starting salaries of lawyers, I believe for the year 2018 or 2019. And so we've got the starting salaries of all the lawyers by university right here. Okay, and so when we've got this, you would think, okay, you've got all these starting salaries, the average starting salary, it should make a really nice, pretty distribution, because regardless of where you go to school, regardless of what you're going into, everyone's getting the same type of job being a lawyer. So therefore, if everyone's getting the same type of job being a lawyer, shouldn't it be a really nice, pretty distribution? And the answer is, let's take a look at this. I'm going to zoom out a little bit so you can see this. The answer is no. Okay. This is the population distribution of the average starting salaries of lawyers. And so this is what you would refer to as bimodal data. You've got a mode right here, and then you've also got a mode right over here. And so we've got a really high concentration over here, and then we've got a really high concentration right here. And the reason why is because you've got these really high quality law schools, and the high quality law schools that are putting out lawyers, if they're going into the private sector, they're getting paid, $180,000 a year starting out. But then everyone else that is either in the public sector of law, or they're not necessarily at one of those super prestigious universities, the average that they're going to make is right around here, which I'm going to zoom in a little bit, which is going to be right around $58,000 a year. So the average starting salary of lawyers is going to be around $58,000 a year until unless you get into the private sector. More specifically, let's take a look at this. We've got the full population data here, the public sector and the private sector, and I'm going to tell you in a minute why I did that. Okay. So the population mean is right here, and the population standard deviation is right there. And so we've got a population mean of 71,299. And then we've got a standard deviation of $33,043.44. And so we've got this distribution, and we can put that into Chebyshev's theorem, and it works all day long. The downside is you really can't use anything except Chebyshev's theorem, and it really doesn't give you the full picture. Oftentimes when you have data that does not perform the way that it should because of issues like this, it's actually better to remove certain pieces of data and say, hey, you know what? This data is so unique that it should be evaluated by itself, but let's take a look at the rest of the data that's not quite as unique. And it's perfectly fine to do that as long as you say that's what you're doing. Don't just take data out and say, oh, we're going to ignore it. Don't ever do that. You need to say, okay, we removed this because that data is so unique that it should be evaluated by itself. And so if you do that, you'll notice, okay, I split it up between public sector and private sector. And so these are the starting salaries, and the reason why I split it up like this, more specifically, is because I've got this spread out exactly where it lands up above, or very close to where it lands up above. This might be just a little bit off, but so you'll see, okay, you've got these people right up here, these people down here, but this is more or less exactly where it lands, and so the charts are kind of just overlaid. So I split it up and I said, hey, I'm only going to analyze public sector, and then I'm only going to analyze private sector. And so what that did is that gave me an actually pretty decent distribution that I could almost consider to be, almost normal. And so I would be able to analyze the public sector data, very easily using a lot higher quality tools, such as the empirical rule. The empirical rule says if your data is normally distributed. What does normally distributed mean? What that means is that it follows this perfectly, normal bell curve, where you've got 68% of the data within one standard deviation, and then you've got 95% of the data within another standard deviation, and 99.7% of the data within 3 standard deviations of the mean. Right up here, the public sector is pretty close to doing that. But for all intents and purposes, it's really hard to find perfect data. So I made a data set right here. And this data set right here is going to be simulated by, let's see here, or this data set right here is representative of weight of ice cream, or better yet, scoops of custard. And this is at like Andes or someplace like that. But so we've got scoops of custard, and so we have the mean. We've got the mode. We've got the mean, and we've got the standard deviation. And so I'm going to give you the mean and the standard deviation right here, and I'm going to do equals average, and I'm going to highlight the entire data set, which is quite a few. Okay, that's 500 records. So that's the average. So the average is right around 5, and then the equals standard deviation of a sample, because we're only taking a sample here. Okay, and it's right about 1. And so what I'm going to do here, I'm going to zoom in and I'm going to show you. I have a mean of about 5 and a standard deviation of 1. And so just for argument's sake, I'm going to just make it 5 and 1. I don't want you to do this, but it's going to make it a lot easier to interpret. So if you have a mean, we're going to put a mean of 5 right at the mean, or right at the midpoint there. So I'm going to make this a little bit bigger. Let's see here. We've got a mean of 5, and then we've got a standard deviation of 1. And so when we have a normal distribution, what we're saying is we've got a 5 right here, and then we're going to have 5 plus 1 is going to be 6, because this line right here stands for 1 standard deviation above the mean. Okay, then right down here, you've got 5 minus 1, so this is going to be 4. And then this is going to be 3, and then this is going to be 2, and then coming up here, 6, 7, and then 8. So you've got the mean. Let me do this. You've got the mean, and you've got mean plus 1 standard deviation. Let's make this a little bit bigger. And then mean plus 2 standard deviations, and then mean plus 3 standard deviations, and then once again coming down here, mean minus 1 standard deviation, mean minus 2 standard deviations, and then mean minus 3 standard deviations. So let's just make sure that we know exactly what we're talking about, right? A standard deviation is the average distance of each observation from the mean. So what we know is that 68%, when data is perfectly normally distributed, 68% of the data falls within 1 standard deviation of the mean. 68% of the data falls within, this area right here. That's what the empirical rule says. If the data is normally distributed, 68% falls within 1 standard deviation of the mean. And then 95% falls within 2 standard deviations plus or minus of the mean. So the really cool thing about this is we can actually add this up. Okay, if I were to ask you, for instance, what percent of custard cones are going to be between 4 to 6 ounces? All that I'd have to do is say, okay, 4 is one standard deviation below, 6 is one standard deviation above. If it's perfectly normally distributed, then there's going to be 68% of custard cones that are between 4 to 6 ounces. Um, or if I were to ask you what percentage of custard cones are between 3 to 5 ounces, I would just take 13.5 plus 34%, um, and then I would just multiply, or I would just add them together, and I'd say, okay, that is going to be 48.5% is between 3 to 5 ounces. Or another thing, if I were to say, okay, we took a look at 200 people who got ice cream cones. Of those 200 people, how many of them, based on this information that we have right here, how many of them had an ice cream cone or a custard cone that's between 3 to 5 ounces? So what we would do is take 13.5 plus 34, and we'd do 200 equals 200 multiplied by 40, let's see, 47.5, or better yet, 0.475. And the reason why is because it's in percentage. So of those, we can say that 95% are right here. Also, 95% are right here because it's symmetrical. Or if I wanted to know what of those 200, how many of them had custard cones between 4 to 6 ounces, I would just change, instead of 47.5%, I would do 68%, because it's 34 plus 34, 68%, and that's 136. 136 of those 200 custard cones is between 4 to 6 ounces. And you can do this with anything, right? You can do this with number of people. You can do this with average wait times. You can do this as long as it's continuous data. You can use this empirical rule if it's continuous data and it's normally distributed. Now, once again, really important, a lot of people make this mistake. They think that the empirical rule ends at 3 standard deviations below and 3 standard deviations above the mean. It does not end there. There is 0.15% that's greater than 3 standard deviations above the mean, and 0.15% that's less than 3 standard deviations below the mean. Because we all know that we all have those really cool days where we go in and we get like a 20-ounce custard cone because the person behind the person behind the counter knows you, and you're like, hey, can I get a big custard cone? And the person's like, yes, I'm going to give you tons of custard. And they give you tons of custard. And then you also have those days when you go in there and you get like this newbie, and they are just afraid to serve you, and then they give you just 2 ounces of custard because they're afraid to drop the custard on the ground. And so it's important to remember this 0.15, remember this 0.15. You can have it as large or as little as you want until it gets down to 0. You can't have it any lower than 0 for this one because you can't have negative custard. But there are some instances where you can deal with negative numbers. So that ends the end of this lecture on the empirical rule and Chebyshev's theorem. Hopefully that was beneficial. And once again, you can download this. You can download this entire workbook down in the description below. So make sure that you remember to do that, so that way you follow along and can do everything that we did. Thanks.